now we actually have to look at how to calculate some concentrations. These concentrations we are calculating are for molarity. This is section 13.3 in your book. Now we have different ways to represent our concentrations. Again, remember they're mixtures, so they're not set ratios, but we can quantitatively define how much is in how much, which is what our concentration calculations are all about. Now again, like I said, there's different units. The one we use primarily, though, is going to be molarity. Notice molarity is abbreviated by a capital M. We've probably seen that a lot when we've gone in lab. We've used 1 molar hydrochloric acid quite a bit. Again, what that molar means, just like it says here, is the amount of solute in moles. So that would be 1 mole of hydrochloric acid in the volume of the solution, in 1 liter of solution. So one thing we have to be careful of is, even though we dissolve most of these things in water, it's not the volume of water necessarily, it's the overall volume. So if I have 1 mole of hydrochloric acid, that's not in 1 liter of water, it's in a lot of water, and part of that volume is going to be our hydrochloric acid. So how do we do these calculations? Well, if we look at what is here, right now, they have an example here about sodium hydroxide. So it says if we have 1 mole of sodium hydroxide, again, sodium's 22.9, oxygen's 16, hydrogen's 1. It has a molar mass of 40 grams. So that is 40 grams per 1 mole. It says if you take this quantity and you dissolve it in enough water to make exactly 1 liter of solution, so we mass out 40 grams, we put it in a volumetric flask, which is what this is. This is my volumetric flask. So there's 40 grams. And then we add some water until we get it up to a 1 liter of solution. Well, that is 40 grams is 1 mole, and that 1 mole is in 1 liter of solution, so we would call that a 1 molar solution of sodium hydroxide. Notice the other example they say, if you take half as much, 20 grams, which would be half a mole, and you put that in 1 liter, now you have a 0.5 molar solution. Okay, so not too terribly hard, but we do have to have some practice with these calculations. Here's one we might want to do here. Let me clear off what I scribbled before. Okay, so we want to know how to make, say we need to make 500 milliliters of a 2 molar sodium hydroxide, which is something I have to do myself in lab all the time when I'm prepping labs. So how do we do this? Well, we have to know again what this means. 2 molar means 2 moles of NaOH in 1 liter of solution. So I need to put in 1 liter of solution there. Well, how much do I want? Well, I want 500 milliliters. So I don't want a liter, right? So I don't want 2 full moles. I want 500 milliliters. So I'm going to put that in next. So 500 milliliters. I'm going to do this conversion in my head, if you don't mind, 0.5 liters. And I'm just going to put that over 1 because it isn't a ratio. It is only in 1. So I can put it over 1. I'll divide by 1. I'm just multiplying them by that value. In my last place now, notice liters have canceled. Now we have it in moles of sodium hydroxide, but I can't measure out moles of sodium hydroxide because it's an amount. I need it in a mass. So I need to know the mass relative to moles. Well, that's the molar mass. So again, just like I said on the previous page, that's about 40 grams per mole. If I put 40 grams of NaOH on top and 1 mole of NaOH on the bottom, now those mole amounts cancel. And what do I get? 2 times 0.5, 1 times 40. So what I need for a 2 molar solution is I need 40 grams of sodium hydroxide. Now an important question again is, how do we make this? Realistically, how do we make this solution? Well, nicely in your book, they have an example of how to make it as far as laboratory procedures. This is for a copper sulfate pentahydrate. Not every day you get to work with a pentahydrate, but 5 waters would be a pentahydrate. So if we want to make this again, we need to make a certain solution. We see what we need to make. It says it wants a 5.5 molar solution. So they took 0.5 times its molar mass to get a certain value, and they'll go and mass that out on the balance, which is what they did here. Now, before you add it to your volumetric flask, like this shows, and it doesn't do a very good job of showing it, but the first thing you want to do typically is, what we want to do is we want to put a little bit of water in the flask, and then we can add our salt, or like it says here, add a little bit of solvent into the volumetric flask and actually add a little bit into that beaker, and then we pour them together. Now we want to rinse all the solute into the volumetric flask, mix it up. Notice it's not full at this point yet. So we have a little bit of water add our solute, maybe add a little bit more water, not all the way full yet. Shake it, shake it, shake it. This is an important step, and I'm going to zoom in on this one. Now we add water up to that line, because remember what we said when we're doing molarity calculations, it is the amount in 1 liter of solution, or 500 milliliters, or an exact amount. So we need to make sure we add an exact amount of water. So in this case, we have to fill it to the line. These volumetric flasks will be graduated, but only to one value. If we go above that value, it's no longer accurate. So we have to make very, very careful, have to be very, very careful when we add water that we don't go over that. Then we mix it up a little bit more, let it stand, and we have our solution made. Often, however, though, you'll notice that after you mix this, and they actually mix together, the volume will go down a little bit, so you might need to add a little bit more water after you've let it sit for a bit. Okay, that's how we practically do it. We can do some calculations, but we also have other calculations, unfortunately. One is molality. So molality, so very similar to molarity, but this is moles of solute now in our mass of solvent, and that mass has to be represented in kilograms. Well, what makes this easy, or perhaps more difficult, is that 1 liter of water has a mass of 1 kilogram. So if we're talking about solutions in water, their molarities and their molalities are going to be the exact same value. They're just going to have different units. Molality is a little m, as opposed to our big M for molarity. Now, I don't really like that. It gets kind of confusing, but that's the way it is, and molality is out there. So often, we're going to have molarities, but occasionally we might have molalities. We just have to be aware of them if they do crop up, and especially we have to be concerned if the mass of our solvent isn't water. Sometimes molalities work very nice to represent values that aren't necessarily dissolved in water, that can be easier categorized as a mass. That, however, even though those are the concentration units listed in your book, those aren't the only concentration units that exist. We also often have a percent by mass. And this is probably what you see in the store when you buy substances. When you buy hydrogen peroxide or acetic vinegar, is they'll have a percent by mass of the chemical that's in them. And that mass is, again, the mass of the solute, what's being dissolved in the mass of the total solution. Again, not the mass of the solvent, the mass of the total solution. So let's see if we could solve a problem. Say we wanted to know what's the molarity of 5% acetic acid. And this is a problem that I have all the time, because if we buy any type of commercial things, it'll be in percentages. But we want them in molarities because we are chemists and we use chemical equations, and 5% doesn't really work well with molar ratios. So what would be the molarity? I should have written the whole question. What would be the molarity of 5% acetic acid solution? Well, let's assume we have a certain amount of solution. Say I take 100 milliliters of that solution. And being that this is a solution in water, we could assume the density of water. So let's assume we have about 100 grams of water. So there are some assumptions there. Hopefully they don't trick us up too much. So we have 100 grams of solution, mostly water. Okay, if it's 5% acetic acid, well, 100 times 0.05, now I just changed my percent into a value, tells me that 5 grams of it is acetic acid. Okay, well, again, that helps me, but again, it doesn't tell me the molarity. So I found the mass, now I want to know the molarity. Well, again, I have to take the 5 grams of acetic acid, so C2H3O2 is acetic acid, and guess what I do? I divide it by its molar mass. So I'm going to divide by the molar mass of acetic acid, C2H3O2. Need to throw the molar mass on the bottom, which for our purposes is approximately 60 grams. Not exactly, but approximately. So now what will I have? Notice grams will cancel. I will have the number of moles, but I won't have the molarity. Remember what molarity is. It is our moles per liter of solution. Well, if we took 100 grams, again, that's my solution. That is 100 milliliters of solution is what I said originally. So I'm going to put this mole amount over a certain volume. So 100 milliliters is 0.1 liters. If I divide it by 0.1 liters, we can calculate the molarity of a 5% acetic acid solution. And the answer there, when I do the calculation, would be we would have a 0.83 molar solution of acetic acid. So pretty low concentration, and I think normally vinegar, when you buy it from the store, is about 5% acetic acid, so it's a pretty small concentration of acid. Not tiny, but pretty small in our terms. Another type of, so what have we had so far? I should stop. In recap, we have molarity, which is by far our most common. In chemistry, we have molality, which we might run into. Again, molality, percent composition, again, is typically what you can see when you buy something commercially. Another one we'll run into, and more with acid and bases, is normality, but I just want to introduce it to you so you're aware of it. Normality, a little bit goofy. What it does is, let's take this example of sulfuric acid, H2SO4. When we put this in water, it's going to dissociate into hydrogen ions and sulfate ions. Okay, but notice there's 2 hydrogen ions, so we have 2 H pluses for every sulfate. So what normality does is normality says, yeah, sulfuric acid is 1 molar sulfuric acid, but it makes twice the concentration of hydrogen ions in solution, and the hydrogen ions, again, are what act as the acid, so that's what people are concerned with. So it's a 1 molar solution, but what we do is we multiply it by the number of positive charges that it puts into the solution. It is really a 2 normal solution of sulfuric acid. So you might see those. Notice, if you had hydrochloric acid, and say you had 6 molar hydrochloric acid, well, when hydrochloric acid dissociates, there's only 1 hydrogen ion for every chlorine ion. So when we look at hydrochloric acid, a 6 molar hydrochloric acid is a 6 normal solution of hydrochloric acid. So, yeah, there you go. Let's look at the section review. What quantity represents the ratio of the number of moles of solute for a given volume of solution? Hopefully we know this is molarity, and this is our most important one. We're going to see the most often. I don't want to say important. We're going to see it the most often. It says we have 5 grams of sugar, and they're dissolved in 1 liter of solution. What is the concentration expressed as a molarity? Well, let's do this. Let's express this as a molarity, a molality, and a percent of composition. So 5 grams of C12H22O11. If we want a molarity, we need moles over liters, so we're going to have to divide this by the molar mass to get moles. So let's look that up. I'm rounding a little bit here, but I'm going to call it 342. It's 342 point something. For our case, it's 342, and this is for sugar. Now I'm going to just abbreviate it sugar. So I'm going to divide by the mass, get the moles. Now we want it in 1 liter of solution, so per liter of solution. Notice we're making 1 liter. That makes that part of the calculation easy. This will give us moles over liters. That is molarity. I get a low concentration, which is fine. This is a huge molar mass, 0.0146 molar solution of sucrose. Okay, now what would that be in molality? Well, in molality, again, it's per kilogram of solution. Well, again, if we're dissolving it in water and a small amount of sugar in that 1 liter of water, we can assume our solution is primarily water. So 1 liter of water is 1 kilogram. So this would also be a 0.0146 molality solution. Molal. Isn't that awesome? How about percent by mass? Well, percent by mass, we don't even need the molar mass to do the percent by mass. We just need the mass over the total mass. Well, again, we said it's 1 liter, but 1 liter of water has a mass of approximately 1 kilogram, like we did with our molality. 1 kilogram is 1,000 grams of water. So if we want a percent by mass, we'd say 5 grams of sugar divided by the solution mass. Again, I'm saying 1,000 grams of water, but it's really 1,000 grams of the solution times 100. So this is a pretty small percent by mass. So that ends it up at a 0.5% sugar solution. So it's good to do all of these. Gives us a good exposure to the different types of concentration units that we may use.